Dear student, today I shall discuss the topic concept of heat and work. So first is, what is the concept of heat? Number one, heat basically it is a form of energy. I repeat, it is a form of energy. Number two, suppose this is the region of high temperature and this is the region of low temperature. So if this is the high temperature, this is low temperature, then what will flow? What will flow? The quantity which flow from higher temperature region to a lower temperature region, that is called heat. That is, it is that quantity which flows from a region of higher temperature to a region of lower temperature. Again, if you rub your hand like this, see, heat is generating. That is, it is produced from work. So what is our number one? Number one is it is a form of energy. Number two, it flows from a region of higher temperature to a region of lower temperature. Number third, it is produced from work. Next, sign of heat. Sign of heat. According to IUPAC convention, heat absorbed by a system is equal to what? And heat released by a system is what? So according to IUPAC system, heat absorbed by a system is a positive quantity and heat released by a system is a negative quantity. Suppose this is our a system. The system absorbed heat, so it is always a plus Q. When heat is released by the system, it is always minus Q. So I repeat, when heat absorbed by a system is regarded as a positive quantity, when heat released by a system is regarded as a negative quantity. So how can you remember this concept? सपोज आपका पॉकेट से कहीं पैसा चला गया, इसको हम नेगेटिव क्वांटिटी कहेंगे. अगर आपका पॉकेट में सामान आ गया तो हमको इसको पॉजिटिव क्वांटिटी कहेंगे. सिमिलर सेम कंसेप्ट, अब मेरा सिस्टम, ये सिस्टम से सम हीट चला गया, सो ये नेगेटिव क्वांटिटी. अगर ये सिस्टम सम हीट आ गया सो इसको हम बोलेंगे पॉजिटिव क्वांटिटी. सो हीट रिलीज बाय अ सिस्टम is a negative quantity, heat absorbed by a system is a positive quantity. Next topic is what is work. Work क्या है? Suppose if you displace a body from this place to this place with the help of a force, by applying some force, that means you have done some work. For example, if you suppose this is our body, this is a body, you displace this body from here to here through a distance dx against the force say fx, the amount of work done is equal to Fx into dx. So it's simple. Work is nothing but force into displacement. Thermodynamic system always consists of a cylinder fitted with a movable, frictionless, weightless piston. That is, this piston can move down, can move up. Now you see, when this piston displaces, there will be work. I repeat, when this piston moves, there is a work. Now let us calculate the expression for the work involved in this type of system. I repeat, whenever this piston moves down, then there will be a work. If the piston moves up, then there will be also work. The next is sign convention of work, or that is, or sign of it, or sign of works. So according to IUPAC, number 1, work done by the system equal to what? Number 2, work done on the system equal to what? See, work done by the system. Suppose myself is a system. I am doing some work. I am doing some work means I have done work at the cost of some energy. I use the energy, that is, I have to utilize some energy. So some energy has lost. That's why when a system does work, energy loss. That's why, since energy is lost, this is a negative quantity. There is work done by a system. Work done by a system. System does work at the cost of energy. That's why it is a negative quantity. So work done by a system is a negative quantity. Work done on the system is a positive quantity. So according to IUPAC, work done by the system is regarded as a negative quantity, and work done on the system is regarded as a positive quantity. So our next topic is pressure volume work, or PV work, or work of expansion. Just now we have seen, when the piston moves up and down, there will be work. Let us consider a cylinder. Let us consider a thermodynamic system consists of a cylinder fitted with a movable, frictionless, weightless piston. This is our piston. Suppose the piston moves up through a distance dl. Suppose this piston moves up through a distance dl against the external pressure, say P external. When the piston moves up through a distance dl against the external pressure P external, now what will be the work involved here? That is our topic. We know pressure equal to force by area. So this is P equal to F by A. Suppose cross-sectional area of the piston is A. Cross-sectional area of the piston is A. Or from this equation we can write F equal to P into A. Now what is the definition of work? Work is force into displacement. Force into displacement. So what is the force here? So force here, this is P into A. What is the displacement here? This is the displacement. DL is the this is the displacement. DL is the displacement. So it is P into this quantity. This quantity, cross-sectional area into this length. Area into length. This is called our dV. This volume has been changed. This is the volume change. So this is the P equal in P dV. So there is W equal to P dV. Since pressure applied on the piston is P external, therefore it is written as Pxt dV. Again, see here the gas expands. This expands, that's why piston moves from here to here. That is, here work is done by the system. Since work is done by the system, so this work should be a negative quantity. Therefore, W equal to we can write minus P external into dV. So these are our expressions for work involved in the expansion or pressure volume work. Similarly, if there is a compression of the work, if the piston moves down, then the work should be a positive quantity. Therefore, W equal to plus P external into dV. Our next topic is work done in an isothermal reversible expansion of an ideal gas. Isothermal means temperature constant. Reversible means the process occurs very slowly. And expansion means work done by the system. So let us consider a cylinder fitted with a frictionless, weightless piston. Let pressure applied on the piston is P external and pressure inside the cylinder is P internal. Let the cylinder contains n moles of ideal gas. Now, let the cross-sectional area of the piston is A. Now you see, if the external pressure and internal pressure is same, the piston will not move. When the external pressure is higher than that of internal pressure, the piston moves down. That is called compression work or work of compression. Now, if the external pressure is lower than that of internal, the gas expands. That is called work of expansion. So, condition number 1, if P external is equal to P internal, no expansion, no work. Second, P external is greater than P internal, external is greater, compression. Number third, P external is less than P internal, then moves up. That is our expansion. So, as per topic, this is the condition here. We know work equal to force into displacement. Now, if the piston moves up, so through a distance dl, which is only possible if the external pressure is lower. Since the process is reversible, the process should occur very slowly. That also possible if the external pressure is decreased or lowered by an infinitesimal amount. I repeat, if the external pressure is lowered or decreased by an infinitesimal amount, say by an amount dp, then the piston moves through a distance dl. So and that in this case, the piston moves a distance dl and acquire a say final volume V2. Initial volume was V1. That is the gas expands from volume V1 to volume V2. So this is the final volume. This is the initial volume. Now, what will be the work for this small displacement? Already we have calculated in the previous lectures. However, here also are calculating again. Force F into displacement is dl. Again we know for pressure equal to force by area, or F equal to P into A. So here P is the P external. So we can write P into A into dl, or since the pressure is external, so we can write P external into P into dl, or since the pressure is since the process is expansion, work done by the system, therefore work should be a negative quantity. Thus we can write pxt into, and this quantity is known as change of volume, small change of volume, that is, so this is not P, this is A. This is A into dl equal to dv. Now, if the pressure, external pressure is decreased by an infinitesimal amount dp, then the piston moves through a distance dl. So now external pressure is become, at this moment the external pressure become, now our external pressure is P external is equal to P internal minus dp amount. So therefore, for this infinitesimal amount decrease of pressure, there is a infinitesimal work, very small work will be there. So work involved due to one infinitesimal step. One infinitesimal step, what will be the work? That is denoted by dw rev is equal to minus P internal minus dp into dv. See this one, dv equal to minus P internal into dv minus minus plus dp in dp dV equal to minus P internal into dV, neglecting this quantity being small quantity. So this is small, we can neglect. Now, so this is the simple work done. We got small work done because of small displacement. So total work done, total work done, or total work involved from V1 to V2. Now what will the total work done? That is, we can get by integrating the W equal to, say, W rev, since the process is reversible, W rev equal to integration of dW rev equal to integration of minus integration from V1 to V2 P internal into dV, or equal to, we can write from here, or W rev equal to minus V1 V2 Pi internal into dV. For n moles of an ideal gas, PV equal to nRT. Here this PV nRT is only applicable for inside the cylinder, therefore it is a P internal. Therefore P internal is equal to nRT by V. Now we can replace this by PINT by this relation. From the equation 1 and 2, we get W rev equal to, just put the values of INT, P internal from this equation. That is, W rev equal to minus integration of V1 to V2 N RT by V dV, or minus, see, N constant, R constant, T constant. So this come out N RT integration of V1 to V2 1 by V dV is equal to minus nRT ln V V1 to V2, since we know integration of 1 by dx is equal to ln x. Therefore we can write directly minus nRT ln V2 by V1. Now replace this ln by log. It should be multiplied by 2.303 is minus 2.303 nRT log V2 by V1. So ultimately we got the relation W rev equal to minus 2.303 nRT log V2 by V1. So which is the required expression of this topic? Again, from Boyle's law we know P1 V1 equal to P2 V2. Therefore P1 by P2 is equal to V2 by V1. Now from this equation we get W rev equal to minus 2.303 nRT log log P1 by P2. So in terms of pressure, we can write another expression. Now for free expansion, that is expansion in vacuum, that is expansion in vacuum, that is in vacuum P external is equal to 0, therefore W rev is equal to minus P external into dV equal to 0 into dV equal to 0. For this is free expansion. For irreversible expansion, W E rev equal to minus P external V2 minus V1. So we have we have derived the expression work done in an isothermal reversible expansion, and also we know the expansion, free expansion as well as irreversible expansion. So thank you very much for watching this video.